Dear students, today we will talk about Cartesian coordinate system. So here we imagine that space is three-dimensional. Therefore, if you have to specify the position of an object or a point, we label three axes x, y, and z. And the position of any point is given by determining its x coordinate, its y coordinate, and its z coordinate. If the position vector is r, it is the straight line that joins the point to the origin. This r is given by xi plus yj plus zk, where all of you understand that x, y, z are the coordinates of the point in this Cartesian coordinate system, and I, j, k are the unit vectors along the direction of x, y, and z. Consequently, we can find that the velocity is time derivative of r. So it is r dot. All of you know these notations on the basis of your previous knowledge of class 11th and 12th. It's quite simple. So it is x dot I plus y dot j plus z dot k. Similarly, if you want to find the acceleration of the particle, that will be double derivative of r, that is d square r by dt square, that is r double dot, that will be x double dot I plus y double dot j plus z double dot k. Right? Now, if the position of the object can be specified in just a plane, then only two axes suffice, an x-axis and a y-axis. Right? The point is here. Its x coordinate is this much and y coordinate is this much. Right? So in that case, we can write that the position vector r is actually xi plus yj only. And then you can find velocity and acceleration in the same manner, right? Now, let us try to see how properly do we define the position vector of a point in a three-dimensional space. Here it's quite easy. The x parameter is this much, the y parameter is this much, so it is xy, so it is xi plus yj. But how do we do it exactly over here? Because we know that our paper is actually two-dimensional. This paper, this board, this is two-dimensional. So how do we exactly specify the x parameter, y parameter, and z parameter of a point which is located in a three-dimensional space? So let's draw the diagram again. So this is the three-dimensional space. This is the point which you are interested in. From this point, you drop a perpendicular. First, let us label the axes as x, y, and z. From this point, you drop a perpendicular in the xz plane, a perpendicular of any suitable length, right? Now, from this point, say Q, you draw a line which is parallel to z-axis and another line which is parallel to x-axis. So this is parallel to this and this is parallel to this. Now this specifies the x coordinate, this specifies the z coordinate, and this much specifies the y coordinate. This point, right? So this is the y coordinate. Therefore, the point P, its position vector will be given by this expression that is already done. But this was only to show you how do we exactly specify the position of a point in a three-dimensional space, because you have to get it connected to all the three axes. So this is the x coordinate, right? This much is the x coordinate, this much is the y coordinate, and this much is the z coordinate, right? And how do you do that? Again, I am repeating that from the point in which you are interested, you drop a perpendicular in the next plane, and from that point you draw two lines which are perpendicular to these parallel to these two axes, and the points where they cut, wherever they cut, they specify the x, y, and z coordinates of this point, right? Now let us also try to understand what are right-handed and left-handed coordinate systems. For example, if in a three-dimensional coordinate system, this is x, y, and z. You move anti-clockwise from x to y. What will be the resultant? So you are moving anti-clockwise. Remember, a clock moves like this. But when you move in this way, it is counterclockwise or anti-clockwise. So when you move anti-clockwise from x to y, the resultant will be along z, but in the outward direction. So this type of coordinate system can be called as a right-handed coordinate system, because you can fix this type of a coordinate system by means of your right hand. This way. One of them is x, one is y, and another is z. Z is straight pointing upwards. So this thumb indicates the z direction, which is pointing outwards, upwards, because we have moved anti-clockwise from x to y. Now, if you move clockwise from y to x, right? So if you move, in another picture we want to show that if we move clockwise from y to x, then again the resultant will be along z, but it will be inwards. It will be inwards. So this type of a system is called as left-handed system, left-handed coordinate system, because you can imagine it with the help of your left hand. Right, now what is the essential difference between a right-handed coordinate system and a left-handed coordinate system? In this system, we move from x to y anti-clockwise. The resultant is along z, but in the outward direction. And in this system, we move from y to x anti-clockwise, and the resultant is along z direction, but inwards. See, you can also imagine, you can also understand this thing by imagining how do we draw a screw inside a wooden plate or a wall. So when you drive the screw inside, you move what? You move clockwise. So where is the direction? It goes in. This is the z direction. This is the screw that you want to put inside the wall. And all of you understand that if we move in the clockwise direction, this way, clockwise direction, what is the resultant? That we are finally able to nail it inside the wall, right? Because you move clockwise. Now when you have to take the screw out, what do? You go anti-clockwise. You keep on rotating it like this, anti-clockwise, and you are able to take it outside, right? So you can also help to understand it by imagining the example of a screw. You want to nail it inside the wall, you go in the clockwise direction and the resultant is inwards. You want to take it out, you go in the anti-clockwise direction and the resultant is outwards. So this is a right-handed system and this is a left-handed system, right? Now let us do some numerical examples to find how do we determine the velocity or acceleration or position of a point which can be specified by means of a three-dimensional Cartesian coordinate system. So let us pick up an easy example. So suppose the x-coordinate of a point is given by 4 sine 2t. I'm randomly choosing any example, and y-coordinate is given by 4 cos 2t, and z-coordinate is given by 6t, where t is the time, right? So how do we find the position? We know that position is given by r vector. All of us know that it is xi plus yj plus zk. So let us write that. What is x? It is 4 sine 2t I times plus 4 cos 2t j vector plus what is z? It is 6t k vector. So this is the position vector. These are the position coordinates x, y and z, and this is the position vector. We have written the position vector. Now what is the velocity? We know that it is dr by dt, time derivative of position vector. So how much is that? Let us differentiate it with respect to time. So differentiation of sine is cos. All of you know that. So in the internal differentiation, this 2 will also come outwards, right? So you will have 8 cos 2t I times. Now differentiation of cos is minus times sine. So this will be minus 8 times sine 2t j plus 6k, right? Because in the differentiation, this t will not survive. You will only be left with 6. Now, if you have to find the magnitude of velocity, We know that magnitude of v will be basically under root of all this square times. It will be 8 cos 2t square times plus minus times 8 sine 2t square times plus 6 square, right? So this will be 64 times 64 will be taken common, right? And inside you have cos square 2t plus sine square 2t, and then you have 6 into 6 36. So this is 1, this much is 1. You are left with 64 plus 36, that is 100, and that is 10 only. 10 meter per second will be the velocity of a particle whose x, y and z coordinates are defined in this manner, right? Now let us try to find what is the magnitude of acceleration. Again, that is dv by dt. You will have to further differentiate the velocity with respect to time. And how much is that? Again, this will get multiplied with this. Differentiation of cos will be minus sine, right? So this will be minus 16 sine of 2t I minus differentiation of sine is cos 16 times cos of 2t j, and here it is a constant now, it will be 0. So if you want to find the magnitude of acceleration, you will square the components. So it is 16 times sine of 2t square plus 16 times cos of 2t square. That's it. So 16 into 16, that is 256. Inside it will be sine square plus cos square, that is 1. So you are left with this much only, and we know that 256 is the square of 16. So acceleration will be 16 meter per second square, right? So similarly, we can take up another example. I hope all of you understand this square term. How does it come out to be? So see, we have done that r is basically how much? Xi, position vector in general, is this much. Now if we want to find its magnitude, how do we do that? So we do that by taking a dot product, right? So if you want to find what is r dot r, so that will be actually xi plus yj plus zk dot product with itself, xi plus yj plus zk, right? So we know that I dot I is 1, this will be x square. We know that I dot j, I dot k, that is 0, right? Then only such terms will survive in which you have I dot I, j dot j and k dot k. The rest of the terms will be 0 in case of dot product. I hope all of you understand that based on your previous knowledge. So this is x square plus y square plus z square, and here it is r dot r, that is r square. So r is how much? Under root x square plus y square plus z square. And we have actually used the same concept over here, because when we square and add the components, this is the concept that we are using, right? So this is the concept that we are using. And how do we obtain it? By taking the dot product of the vector with itself, and we get its magnitude, only the numerical value, right? That is why to obtain the magnitude of velocity and acceleration or even position, we can just square and add the components under root, right? So I hope all of you understand that. Now let us move to a next example. Suppose you want to find, in the next example, suppose you want to find what is the position or velocity and acceleration of a particle whose position vector is given by, randomly I'm choosing anything. Suppose you have this r vector, this is 4 by 3, anything, t cube minus 2t I plus say anything, suppose 60 square j, I'm choosing anything. So you have to find what is the velocity and acceleration of a particle whose position vector is given by this equation at time t equal to 3 seconds. So when the particle begins its motion, what will be its velocity and acceleration after 3 seconds, right? It's quite easy to find. Now I'm doing all these things because you are beginners in your first semester course, but gradually you should get habitual with this. You should be able to do it of your own as well. Now, what is velocity? It is dr by dt. It is how much? Obviously, in the differentiation, the power comes down and one power gets reduced. All of you know that 3 and 3 will get cancelled. You are left with 4t square minus 2. This is the I component, plus that is 12t j. Now what is acceleration? It is dv by dt, right? So what is that? Again, you are going to differentiate it. It is 8t. This will not survive. 8ti only, plus this will be 12 only, 12j. Now once you are asked to find the value of this acceleration at time t equal to 3 seconds, so what do? You basically take the root component as well, right? So you can, how much is this? So velocity, its magnitude is how much? Obviously it is 4t minus 2, 4t square minus 2 square plus 12t square, because it is the magnitude only now. And acceleration, it is how much? It is 8t square plus 12 square, right? So once you solve it, you also put the value of t, how much? 3 seconds, and whatever is the answer, that is the resultant value, right? So this is how you are going to solve such kind of numerical problems, and that gives you a basic idea of Cartesian coordinate system. So that's all.